Good day again. Welcome to another tutorial by M.I.B. Math is Beautiful. And today we'll be looking at math proofs by mathematical induction. Actually, this is a continuation from part 1 of proofs by mathematical induction. Now, just to recap, in that tutorial, we just explained the basis of mathematical induction, and we showed the steps involved in proving mathematical induction. And the steps involved are: 1, you want to prove true for n equals 1. 2, you want to assume true for a different number, which is n equals k. 3, you are required to prove true for n equals k plus 1 using the case in step 2, which was when you assumed true for n equals k. And then the fourth step is that once step 3 has been proven true, where once you have proven true for n equals k plus 1, then it should be concluded that the initial statement is true for all positive integers. Now, and in looking at the basis of mathematical induction, we actually reasoned that the basis of mathematical induction was like a train of dominoes, where the first thing you actually do is to prove true for n equal 1 based on the step. Once you have proven true for n equal 1, then this domino will actually hit the subsequent domino, which is n equals 2, and create a train or domino effect. Right? Then we move on to step 2, where we assume true for a different number n equals k. So right here you can see we shaded n equals k because this is a different domino. So this is actually assumed true. Once it is assumed true, then this will actually fall as well. And if this falls, then it should hit n equals k plus 1. And that is where we are at now, step 3. Once you're at step 3, which is n equals k plus 1, you will actually look to prove true, or prove that this is actually true, where n equals k plus 1. Now, if this is proven true, then this domino will indeed fall once n equals k hits it, right? So if this domino falls, then it will actually hit the subsequent, which is n equals k plus 2. And it should be reasoned that this effect will continue to the end of whatever domino is in the train. Now, prove by mathematical induction that the summation from r equals 1 to n of r squared is equals to 1/6 of n times n plus 1 times 2n plus 1. Right? Now the first step, as I have indicated, is to prove true for n equals 1. Right? So where n equals 1, you put 1 in the formula. And this will actually get 1 squared, where in this case n would be equals to r equals 1. So because if n is equals to 1, then it will actually be the same as r equals 1. So this would be 1 squared is equals to 1 over 6 times 1 times 1 plus 1 times 2 times 1 plus 1. And then this would actually be 1/6 of 2 of 3, and 1 squared is actually 1, is equals to 1/6 of 6. So 1 is equals to 1. Therefore, proven true. Now, step 2 is to assume true for n equals k. So all we'll be doing is that we'll be replacing n equals k in the formula and assuming it to be true. So this will actually be the sum of r equals 1 to k of r squared is equals to 1/6 k plus 1 to k plus 1. Right? Right? Now, once you assume true for n equals k plus 1, the third step is that you are required to prove true for n equals k plus 1. Right? So that is the sum of r equals 1 to k plus 1 of r squared is equals to 1/6. And anywhere k is, you put k plus 1, so this will be k plus 1 k plus 2 and 2k plus 3. That is, you replace n equals k plus 1 in the formula here. So this would be k replaced by k plus 1. K plus 1 would be k plus 2. And k plus 1 would have been 2k plus 2 plus 1, which is 2k plus 3. Right? So you're required to prove true for this. Now, this is what you actually want to prove true. Because once you put k plus 1, this is what you should get. So you're going to use the case in step 2 to prove true for k plus 1. Now, note that the sum from r equals 1 to k plus 1 of r squared, right? This is the same thing as the sum from, if you're summing from r equals 1 to k of r squared plus the k plus 1th term, right? So you're summing from r equals 1 to k plus 1 of r squared. So if I were to sum from r equals 1 to k, which is the k is the previous the previous term before k plus 1, then I can sum from r equals 1 to k of the function, then add the last or the k plus 1th term to get this, right? Good. Now, once you do that, you should also recall, so we're going to work this question, you're going to recall that the sum of r equals 1 to k of r squared is equals to what? 1/6. Now this is when you're using the step 2 to actually prove n equals k plus 1. So this is where step 2 comes in, because you're recalling that r equals 1 from the, you're recalling that the summation of r equals 1 to k of r squared is actually equal to 1/6 k plus 1 2k plus 1, right? Now the k plus 1th term is basically k plus 1 all squared, because if you're putting k plus 1 anywhere r is, then this would actually be k plus 1 all squared, and that will actually be the k plus 1th term, because remember, all the terms in this series is denoted by the function, or is governed by the function of r squared. So if you're looking at when r is equal to 1, the first term would actually be 1 squared. If you're looking at when r is equals to 10, then the 10th term would actually be 10 squared. So if you're looking at the k plus 1th term, then the k plus 1th term would actually be k plus 1 squared, right? Now if we were to put these together to get the summation of r equals 1 to k plus 1 of r squared, then this would actually be, so the sum of r equals 1 to k plus 1 of r squared would actually would be equal to 1/6 k plus 1 2k plus 1 plus k plus 1 all squared, right? And then we move to simplify this expression, right? Then this would actually be looking at what is common to both. We're actually factorizing this. The common is the constant, which is 1/6, and also k plus 1, right? Then what would be left is, from here it would be k and 2k plus 1, plus from here it will actually be 6 and 1 of the k plus 1 term, so that would be that, right? Good. And then now you simply simplify the expression. So this would equal to the sum of r equals 1 to k plus 1 of r squared is equals to 1/6 k plus 1. And then looking at this, you'd actually get 2k squared plus 4k plus 3k plus 6, right? And if we should simplify further, r equals 1 to k plus 1 of r squared, this will equal to 1 6 k plus 1, and then factorizing this expression is actually k plus 2 and 2k plus 3, hence proven true. Correct? Now you can see that this here is the same as what we were required to prove true. So we were required to prove true for n equals k plus 1, which is this here, which is this summation here from r equals 1 to k plus 1 of r squared, which equaled 1/6 of k plus 1, k plus 2, 2k plus 3. And you see from all the steps that we have taken, we actually proved true. We got back the same thing. So therefore, this is proven true, right? So all we need now is our closing statement that since you have proved it true for n equals 1, and you have proven true for n equals k plus 1, then for all n, which is an element of integers, or element of natural numbers, sorry, the expression actually holds. Thanks for watching this video. Please like, subscribe, hit the notification bell, leave your comments, and visit us on Facebook at M.I.B. Math is Beautiful.